Hi, everybody. My name is Yisrael Mirsky. I'm a PhD student at Ben-Gurion University. I'm going to present to you Kitsune. The co-authors are Tomer Deutschmann, Yuvalovich, and Asaf Shabtai. So neural networks, as we know, are great at detecting malicious packets. And we've seen great results in literature. And the main reason for this is because neural networks can detect nonlinear patterns and learn all sorts of different kinds of complex behaviors. But a question comes to mind, why don't we see neural networks put in NIDSs, network intrusion detection systems, more often? So why don't we see snort plugins that use neural networks have been trained previously to detect new or emerging threats? So the main reason is because most of the work done with neural networks in intrusion detection has been done in a supervised manner. In other words, they're trying to train a classifier to try and detect different threats. And just run through a use case so you see all the different challenges. So in order to build such a classifier, first you have to collect all the packets. You have to label them being malicious or normal, train a deep neural network on the labeled data, deploy the neural network on the device, and execute them on every single packet. And finally, when a new attack is discovered, go all the way back to 1. So it's very clear already what the challenges are. But let's just look at a few. So for collecting packets, you need a very large database. And you need many samples of each kind of malicious packet in order to avoid the problem of imbalance. For the labeling, you need an expert with a lot of time to go through all the packets. You need a large GPU server, so we can't deploy this just on any router. We need to first train it on a server. And we need, for the executing part, we need to be able to handle thousands of packets at a time. So the execution has to be really fast. And just giving you an idea, executing a autoencoder with 15 layers, 17 layers on a Raspberry Pi, given 115 input features, takes something like 2 to 3 milliseconds. So that's about like 500 packets per second. So it's not very high. So we need a very kind of like a plug-and-play solution, not too much iterations in the training phase, and we're looking for something that's very fast and efficient to execute. So we offer Kitsune, and Kitsune is a network intrusion detection system which uses an ensemble of autoencoders, neural networks, to detect anomalies in network traffic. So the advantages of Kitsune is that it's unsupervised, so we don't need to label, we just need to train from the regular traffic. It's online, so all the training and execution is done on a per packet basis, so we don't need to store and aggregate packets. And it's plug and play, so we can just put it on a device to train on site. And it's lightweight. We use a new approach to the architecture of autoencoders and detecting anomalies, which we'll go into detail later on. OK, so how does the framework look? So this is the classic NIDS setup. So you have an NIDS set up on a gateway, on a server, or on some sort of other dedicated device. A packet arrives. The NIDS takes a look at this packet, perhaps a sequence of these packets in a TCP stream, and then makes a log, decides whether it's malicious or not based off an anomaly detection algorithm or a set of rules. So the Kitsune framework has two main components. So you have the external libraries for packet capture. So you can use either NFQ or AF packet. We typically use NFQ. And for packet parsing, we use packet++. We can also use Scapy and Python. Then once we have a representation of a parsed packet, Kitsune has then two subcomponents. So the first subcomponent is the feature extractor, where we extract 115 features, which represent that packet and kind of like a statistical snapshot representation of where that packet came from and its channel. And that representation, that feature vector, is then passed to our anomaly detector, which we call KitNET. So let's first talk about the feature extractor, and then we'll talk about the anomaly detector. So the feature extractor uses something called dampened incremental statistics. And just to give you a quick background on what that is, so let's say we have an unbounded stream of values, and associated with each value, we have a timestamp. And this could be, for example, a sequence of packet sizes. So our objective is to compute all sorts of statistics or feature for our machine learning algorithms, such as mean and standard deviation, over a recent history of S, given limited memory and non-uniform sample rates. So the simplest way of doing this, we can form an object called the incremental statistic. And we can have it in n, which is the number of observations seen so far, LS linear sum, SS the sum squares, and SR sum residuals. And we can compute all sorts of different basic statistics at any time, such as the mean standard deviation, quite trivially. And to update the incremental statistic, we just perform this simple incremental update quite simply. But the problem with doing it this way is that now we're tracking the entire history of the stream. We're not interested in the entire history of any, for example, IP stream. We just want to know what's happening in the last moment, history or time window going back. So we use an approach used in stream clustering, which is to apply a decay factor. And it's kind of like a penalty that causes the incremental statistics to forget information over time. And thus, we kind of capture a small window going back. So the changes are quite small. We just change n to w, which is a weight. We keep track of the last timestamp when we updated the incremental statistic, change every n to w. And before we update an incremental statistic, we compute the decay factor, which is basically a function based off the amount of time that has passed since the last update. And then we scale each component before performing the update. So from any stream, we can extract about 7 different features. So we have from a single stream, we can extract the weight, mean, standard deviation. If we want to compute two-dimensional statistics, we can take a look at between 2 streams, magnitude, radius, covariance, and correlation coefficient. OK, so now how are these incremental statistics apply to network traffic? So we identified 5 different streams. The first stream is the packet sizes coming from a particular MAC IP source. The packet sizes in general coming from an IP address. The jitter of the traffic coming from an IP. This is very helpful in detecting, for example, man-middle attacks. The packet sizes between any 2 IPs and the packet sizes between any 2 sockets. So when a packet arrives, we extract 23 features. So that's 3 features from each of the 1-dimensional streams and 7 features from each of the 2-dimensional streams, totaling the 23 features. And we don't just take a look at one window going back, so that'd be, let's say, 1 lambda. So we want to look at several windows going back. So for example, we want to know what happened in the last microsecond, the last millisecond, the last second, and so on. So in total, for each packet, or each stream, if you will, we track 5 different incremental statistics over different windows and extract a total of 115 features from each packet. And again, these 115 features kind of capture a snapshot of what's happening in this channel and what that host that sent that packet is doing. OK, so now we know how our feature looks like. Now, how do we perform the anomaly detection? So for the anomaly detection, we use an autoencoder. An autoencoder is a neural network which is trained to reproduce its input after some sort of compression. And that can be performed online in the following way. So first, we have a training phase. In the training phase, an observation arrives and perform forward propagation. And then we compute the error, where the error is the difference between the input and the predicted output. And the predicted output, we're trying to reconstruct the same input. OK? Then the reconstruction error is then propagated backwards in backpropagation. And we use stochastic gradient descent to perform an incremental update. And so that way, we don't need to hold more than 1 observation at a time. Then after we've trained the neural network enough, we then move over to the execution phase, where whenever we perform, whenever a new observation comes, we perform forward propagation. And we measure the reconstruction error. And the reconstruction error tells us the following. If we have a large reconstruction error, that means that the autoencoder has not seen this concept before, and therefore X is an anomaly. And if it's a low value, then we say that the network is able to reconstruct this concept after the compression, and therefore it is a known concept, and therefore the X is not an anomaly. It's normal. OK, so now the burning question, why not just one big, deep autoencoder? We kind of mentioned this before, and there's 2 reasons. One is the curse of dimensionality. And the other is the problem with the training execution complexity. We want to be able to train our neural network on site, let's say on a simple router, and we also want to be able to execute it. So executing is also a problem when you have a deep neural network. If you have a very simple device, it's very challenging because you need to keep up with so many packets per second. So we know that the complexity of a neural network increases exponentially the larger the layers are. So our solution is, why don't we just partition the feature space into smaller sections, and then feed each of those groupings into smaller autoencoders, which are It's much, much easier to execute and train. And then what happens is that each of these autoencoders are going to basically be in charge with reconstructing those components. And they will produce each one of them their own reconstruction errors, sort of forwarded to an output layer. And the output layer is in charge of kind of understanding or learning the relationship between these groupings and output a final anomaly score. So that's the general idea of KitNET and our anomaly detection framework. But the question is, how exactly do you find these groupings, and especially online? Again, we want to do everything kind of in a plug-and-play manner. So what we want to do is we want to find these correlated groups of features. So each group of correlated features will be a single autoencoder. So how do you find those online? So very briefly, because unfortunately I don't have time to go into it, please feel free to find me afterwards or take a look at our paper. We keep track of a distance matrix, which measures the correlation distance between any two features. So we have 115 features, so the matrix is very reasonable to keep track of. And we keep track of this matrix during the training phase. And at some point, we perform a one-time agglomerative hierarchical clustering, where we can then identify groups of correlated features, and then assign an autoencoder to each of these groupings. OK, so moving over to the experimental results. So we took a look at two networks. We took a look at a surveillance network. The surveillance network had about 8 HD cameras sending continuous streams and several other hosts with DVRs and so on. And we also took a look at an IoT network filled with all sorts of different kinds of IoT devices. In both cases, we applied Kitsune at the gateway. So we saw all traffic going in and out of the network. So for the algorithms, we took a look at signature-based NIDS. So we took a look at suricata. It's like snort, but parallelized. And we gave suricata 13,000 emerging threat rules to detect all sorts of different new attacks. For the algorithmic side, we took a look at, for anomaly-based detection, we took a look at batch algorithms, such as a Gaussian mixture model and isolation forest. And for online algorithms, we took a look at PC stream and the incremental Gaussian mixture model. So although our algorithm is online, so it makes most sense to compare to other online algorithms, we also took a look at batch-based anomaly detection algorithms, because it's a good baseline to understand how well are we performing to the best case scenario. So for the attacks, we took a look at the numerous kinds of attacks, ranging from OS scanning, video injection, SSDB flooding, and the Mariah botnet malware. And in all cases, we trained our neural network, or Kitsune, the framework, for about a half hour. And then afterwards, we subjected it to all sorts of benign and malicious traffic. So in summary of these results, I'm not going to go too much into detail, in general, we found that Kitsune was very good at, much better than other online anomaly detection algorithms, and was at par and sometimes even better than batch-based algorithms. And we also found that, more interestingly, that it was actually much, much faster than the other approaches. We've got about 20,000 packets per second on a Raspberry Pi, and about 140,000 packets per second on a desktop PC. And these results vary depending on the results of the clustering, of course. So if you happen to have a very large autoencoder in the end, you'll have a little more complexity added to the processing. So that's why during the clustering process, you can actually give as a parameter the maximum size you want for any autoencoder to kind of cap that complexity value. So in summary, in past, most network intrusion detection systems have been using, or in related works, have been using classifiers to perform detection. And we suggest that actually you should be using autoencoders to perform anomaly detection, simply because it eliminates the problem of labeling data, and it enables plug and play. And we show this with our Kitsune framework by the efficient feature extraction framework, which we propose, and the efficient anomaly detection algorithm for the online and on-site learning and execution. If anybody's interested in downloading our algorithm, we have the core anomaly detection KitNET you can download from GitHub. And if any questions, please feel free to ask now.
Hi, very interesting work. I know a lot of the commercial space, the next generation firewalls claim to do anomaly detection, not with neural networks. Have you tried comparing your results to what those commercial tools are doing?
No, we have not. We only compare it to the signature-based solutions.
Yeah, that would be interesting to see that result at some point if you do that comparison.
Tobias Fiebig, TU Delft. I was wondering whether
Sorry, I don't hear.
Tobias Fiebig, TU Delft. I was wondering whether you performed an analysis on false positives, false negatives, also on high packet throughput networks. So I think in the paper you're having like around 500 PPS for the experiments.
I'm sorry, it's very hard for me to hear you.
I was wondering whether you performed the false positive, false negative, etc. evaluation also on high throughput networks.
High-speed networks?
High throughput. So with the rates you have in table 3 in your paper, I think it's like around 500 PPS, if I was not mistaken. So
I'm not sure if I fully understand the question. We perform, if the question is how efficient the algorithm is, or?
yes, how well it works when you have more packet throughput than in the experiments you're referencing in the paper.
Okay. So, well, we performed several benchmarks on a Raspberry Pi just to give an idea of how well it would work on a simple device. And we got something around, like I mentioned earlier, something like about 10,000 packets per second, somewhere in that range.
500?
Sorry?
500?
No, 10,000.
So 8 minutes with 1 million packets?
So for just giving you an idea, so for 8 HD surveillance cameras, you can produce something like 8 million packets an hour or more, and we barely use like 5% of the CPU when processing those packets.
Well, thank you.
Okay.
I have a question. Giovanni Vigna from UC Santa Barbara. I think that comparing an anomaly detection system with a system based on signature is sort of like, apples to oranges.
Right.
Have you tried to, it seems that the attacks that you're detecting are mostly volumetric, so they produce a lot of traffic. Have you tried to see how effective it would be just to have a very simple threshold system that would detect, DOS attacks that produce a lot of traffic without the need for something so sophisticated?
Right. So we compared. I mean, we also compared other anomaly detection algorithms, and for example, we could try, cum-sum to try and cumulative sum to try and detect statistical deviations. And in most cases, for any really obvious attacks, for example, flooding of any sort, like SYN flooding, you're going to detect it very quickly, very easily. But excuse me. But for some of the attacks, such as ARP spoofing, things that are very sporadic, or video injection is a very good example. So one of the attacks that we did was we intervened as a man in the middle and cut out the video and re-injected our own video into the video stream. So even those kind of attacks we're able to detect quite nicely.
Thank you.
Bimal from UC Santa Barbara. So I have a question regarding a technique. So do you have a sense for how much your performance is due to the feature extraction versus your autoencoder algorithm? So in other words, if you were to replace the autoencoder with a classical supervised or anomaly detection algorithm like one class SVM or a PCA algorithm, do you think you'll get comparable performance or worse or better?
Right. So I mean, executing SVM is very, very cheap. But also part of that consideration is training it as well. So training SVM, you can only do batch. I mean, there are some incremental implementations, but in general, it's a batch type training algorithm. And we were really aiming for something that you can train on site as well as execute. So that kind of limits the scope quite significantly. Comparing the execution time, it's actually, I mean, it's not going to be as cheap as an SVM or even a simple small autoencoder, but considering that we value the 115 features that we're extracting and we want to use that to try and determine if there's some sort of anomalous behavior happening in the channel, the complexity is still going to be quite up there. I don't have any exact values to give you, but I hope that gives you a better idea.
Okay, thank you.
Hi, thank you for your talk. Pablo Mariano from Indiana University. So once you define the root mean square error of this time series, how do you define a threshold to label one of these points as anomalous or not?
That's an excellent question. I forgot to mention that during the talk. Thank you for bringing it up. So actually what we do is we found that from this particular network, you get something like a log normal distribution. So you can fit it to a log normal distribution, and then you can just set a probability as a cutoff threshold. You can use more advanced techniques, such as like kind of take a sample and build a Gaussian mixture model, or you can use some sort of other histogrammic method.
Okay, thanks.
Okay, I think our